start sharing my screen. Okay. So welcome everyone to the first real lecture of this week. So I will be talking about Gaussian elimination, and it is possible that a number of you have seen this in some form or the other before. Okay, but it is also possible that some of you haven't. So before I even start going ahead, can we get a quick raised hand count of people who have seen Gaussian elimination in some form before? You must have heard about row reduction or row echelon form or solving a system of equations. If you have heard any of these before and have done at least one example by hand, then you can raise your hand and maybe Sai or somebody can give me a count. Is that right? Have people heard this before?
No, only two of us have.
Oh, okay. All right. So that is a good thing to know, because then I know how much detail I should go into. Okay. All right. Thank you everyone for responding. So, so let me begin with a very simple problem that you must have seen in school also. So suppose you have two pieces of information which you can, some word problem, like chocolate costs. There are two kinds of varieties of chocolates, and they cost some A and B. Okay, that is one piece of information, and you have X, some K amount of money. Okay, so suppose now if I write it in terms of an example. Okay, so okay, so suppose I tell you that I have an equation, say x minus 2y equals 1. Okay, so x and y are some variables. Okay, and they follow this equation. There's one more. Okay, there's also 2x plus 3y equal to say 9. Okay, so I have these two, and I simply want to find x and y that satisfy both these equations simultaneously. That satisfy both equations simultaneously, means at the same time. Both have to be satisfied by the same pair x and y. Okay, then one of the easiest way, or if you are pressed to come up with a method, I think the method that you will come up with is you eliminate one of the variable, right? So you look at the first equation, say, and then you say, okay, from that equation we know x equals 1 minus 2y. Okay, and then this x you substitute in this second equation, so that second equation is now entirely in terms of y, right? So you put 2 times, instead of x you put 1 minus twice y plus 3y equals 9. And now what you have is one equation in one variable, which you can hopefully solve, right? So if I do this like maybe like a 5th grader or something, so this will be 2 minus 4y plus 3y equals 9. And so this will be minus y plus 2 equals 9. So minus y equals 7, and therefore y equals minus 7.
X is equal to 1 plus 2y, right? I think.
X is equal to 1 plus 2y. Yes, I knew I was making some mistake. Okay, so so this is going to be a plus, and then that's going to change everything. So I will have 7y plus 2 equals 9. So that means 7y equals 7. Therefore, y equals 1. Okay, and so if I know y equals 1 now, I can use this information and substitute it back here, okay, to give me that x, which is supposed to be 1 plus twice y, is now equal to 1 plus, so y is 1, so that's 3. Okay, so I get the answer x equals 3, y equals 1. And now if you go back and check then these values of x and y will satisfy both these equations. Okay, so I have found a pair x comma y which satisfies both equations simultaneously. Okay, that is what we mean. So this, whatever we did here was the same thing can also be termed as solving this system of equations. Okay, so you can call this process is called solving the given system of equations okay, and the method that we used here, okay, everything that we did here, if you think of it, we eliminated one variable, right? We eliminated the variable x by making this kind of substitution. Okay, so we eliminated the variable x, and so this method is called the method of elimination. Okay, so we are solving this given system of equations using elimination. That's what we will say. Okay, so I'm writing this out because this is the, you might be doing this process. Okay, you might be knowing this entire process already. But if somebody says it in this language, you might not recognize. So that's why I'm writing it out in words so that it's also part of the language. You need to know this language so that, everybody, when everybody speaks in that same language, then the ideas can be conveyed more easily. Okay. All right. So this is what we have done here. We have solved a system of equations. These were two equations in two variables, right? So this was a system of equations, system of two equations in two variables. So let me write that. So this is a system of two equations in two variables. Okay, and so now what I want to do is I want to look at this system of equations a bit more closely. Okay, so there are two ways of viewing this system. One way is just the way that we have written it here. Okay, which is you look at this one equation and you look at this other equation. Okay, so I'm looking at this sort of a row wise. Okay, and now each of these equations, if you remember some coordinate geometry, if you've done some coordinate geometry, equations of lines and all. So I hope if somebody has not seen coordinate geometry or equations of lines, then they should kindly raise their hand. Okay, otherwise I will not know. And I'll assume that you have seen equations of lines before. Everybody has seen equations
I think
of
everyone,
lines?
everyone
Okay.
has seen
Okay, that's
it.
wonderful. So here what we have, you can think of this as two equations of two lines here, right? So you have on the one hand, you have x minus 2y equals 1. And on the other hand, you have the line 2x plus 3y equals 9. Okay. And if you want to find x and y that lie on both these lines, it's like saying you want to find the point of intersection of these two lines, right? So geometrically, what you have done when you solve this system of equations, so geometrically, this amounts to the following. So you look at the lines. Okay, so this is my origin here, 0, 0. Okay, so I'll just say 0, 1, 2, 3. Let's say, yeah, my solution is 3, 1. So 3 is enough for me here, and then 1, 2, 3. Okay, so the first equation, x minus 2y equal to 1, right? So what is the sort of the easier thing here is to find its x-intercept, right? So what is the x-intercept of this line? So I'm looking at x minus 2y equal to 1. So that is same as looking at the equation y equals So 1 minus x divided by minus 2, right? So this means y equals x by 2 minus 1 by 2. X by 2 minus 1 by 2, right? But you can find easily the x-intercept of this by just putting y equal to 0, right? So the x-intercept is 1 and the slope is half. Okay. So you with some more information, you can also like draw this line. Okay. So since the x-intercept is 1, I'm just going to draw it. Okay. So some line like this. This is the line x minus 2y equal to 1. Similarly, I can plot the other equation here, 2x plus 3y equals 9. Okay, so with similar analysis, you can solve this. You can find in this case the y-intercept will turn out to be 3, right? If you put x equal to 0, the y-intercept y equals 3. So 0 comma 3 lies on this line. So the y-intercept is 3, and then you can, what we have shown now is that these two lines actually intersect in the point 3 comma 1. Okay, so so the way I drew it here, I don't have 3 comma 1 on that line, so I should just erase this and draw a better picture. So I want 3 comma 1. This is on the line x minus 2y equals 1. So now let me just join these 2 points and yeah. Oh, all right. So that's my line x minus 2y equal to 1, and the other line 2x plus 3y equals 9 has y-intercept at 3, and it also passes through this line. So I hope that will be straight. Yes. Okay. So this is my other line, 2x plus 3y equals 9. And this here is the intersection point 3 comma 1. Okay. So this is what it amounts to geometrically. And I think this is something up to here, this is something that you must have seen in school in some language or the other. Okay, you might have used this system of equations to find the point of intersection, right? So this is possibly something you have seen. Now what we want to do is we want to take this idea and generalize it to when you have more equations and more variables. Okay, so right now we were dealing with only 2 equations and 2 variables, but in real life problems, systems of equations are generated by the thousands, and their dimensions could be, really, really large, million by million or whatever, does not have to be square even. So, so if you want to solve systems of equations that large, then you need to generate some really elegant algorithms or quick algorithms and algorithms that you can trust in the presence of rounding errors, right? So the first step is to try and understand the elimination process mathematically and see how it will lead us to some basic pseudocode. Okay. All right, so now what I'm going to do is rephrase this problem slightly in terms of vectors. Okay, and because that language will help us when we take this problem to more number of variables. Okay, so what I'm going to do now is these 2 equations here, I'm going to rewrite in a slightly different manner. Okay, so now we are trying to change the language slightly. Okay, or we are trying to build new language. Well, this is new for some of you. It's not new mathematically. It's been around for lots and lots of years. So what we want to do is this x minus 2y equal to 1 and 2x plus 3y equal to 9. Instead of writing it like this, I'm going to write it in the following way. So the coefficients of x and y, I'm going to collect in the rows and columns. Okay, so the first equation I'm going to write as 1 minus 2. These are coefficients of x and y, right? And in the second equation, the coefficients of x and y are 2 and 3 respectively. Okay. These coefficients I'm going to collect in this coefficient matrix. This is called a matrix. The matrix is nothing but array, okay, rows and columns filled with some numbers. Okay, that's a matrix. So this is this I will call the coefficient matrix. Okay, and the variables I will write here x and y. Okay, equals the right hand side I will just express here. Okay, now why can you write these equations in this form? Okay, the answer to that is matrix multiplication. You can write them like this because if you so matrix multiplication, again something that I don't know how many of you have seen before. So can we have a quick raised hand count for
So it was given in the pre-reading material, so everyone is expected to know about matrix multiplications.
Okay, so I will assume that you have heard about matrix multiplication. Thank you, Sai. And then so if you just multiply this out, this is 1 times x minus 2 times y equal to 1. So the way you do it is you just equate the first row of the right hand side with the first row of the first row of the left hand side with the first row of the right hand side. And then so if you matrix multiply these two, so this is a 2 by 2, this is a 2 by 2 matrix. This is a 2 by 1 matrix. And so if you multiply out these two, okay, then the resulting matrix is x minus 2y and 2x plus 3y. Okay, and the dimensions match up according to expectations, right? 2 by 2 multiplied by 2 by 1 is 2 by 1. That's what we have here. And then you just equate the first row with the first row, that gives you the first equation. Second row with the second row, that gives you the second equation. Okay. So what we have done is we have written this system of equations in terms of matrices like this. Okay. And now what we want to do is, sorry, why won't I get a new page? Just doing this should give me a new page. Okay, sorry, just add. All right, so then oh yes, I know what happened. I'm sorry, just one moment. Yeah, yes, there we are. So now, so this is one way of doing it. Okay, so you have written these equations as some matrix times all the variables in a column. Okay, this is a column. We call this as a column. Similarly, this is also a column. Column or column vector, either way. If I say column, it means column vector. Okay. So you have written all the variables x and y here in a column or a column vector. Okay, and you have written the right hand side also as a column vector and the coefficients in a coefficient matrix. Okay. Now, but there is one more thing that you can do. Okay, so this was one expression. Another expression that you can have is the following. Okay, so this is the row expression. This is row expression written as matrix or written in matrix form. And one more way of expressing this whole business is what I will call the column expression. Okay, because the same equations I can write in the following way. What I can do is I can see this is variable x in both places, right? So this is 1 times x, 2 times x. I can write this as x times the vector 1, 2. Okay, plus y times the vector minus 2, 3. equals the vector 1, 9. Okay, so now what have I done here? I have expressed these equations, okay, as x times a column vector plus y times a column vector equal to a column vector. Okay, so this is expressed as a sum of vectors, right? So all these here, this one, and this one are vectors. Okay, if you like, then these are vectors in R2. I hope the notation R2 is everybody knows. If and somebody doesn't know, just let me know. This is nothing but your XY plane R2. You know that every point in the plane has an address, right? So if I pick up any point in the plane, what is the address of this point? You can express it by finding, you drop a perpendicular on the x-axis, you drop a perpendicular on the y-axis. The values that you get for x and y, those numbers, give the address of this point. That's where this point lives. Okay, so every point in the plane in this way has this address. You can write it as x comma y, and if you want to write it in vector form, you can write it as the column xy. Correct? So that is exactly what I have done here. Okay, sorry, I should not use the same notation everywhere. I should have called this A and B because this is not the same x and y that we are using in the example. So let me just change that. I'll call this A comma B. Okay, this is A, this is B. And the same thing you can express as a vector. And so here, what we have done is we have written this system of equations that we had up here in terms of a sum of vectors with some coefficients. X and Y here are now coefficients. Okay, so this is an expression as a linear combination. So I would like to ask Adityan if he could talk about linear combination in his lectures already. Expression as linear combination of the vectors 1, 2 and -2, 3. Okay, and so what we are saying here is that solving this system of equations is like solving this vector equation, where you are saying that you want to find x and y such that x times this vector plus y times this vector gives you the vector 1, 9. Okay, and why do we want to do this? We want to do this because this language will help us in higher dimensions. This is the language that we will use. Okay, and so geometrically now, so here the row expression led to these two lines, correct? If you want to look at this in 3D coordinate geometry or as vector geometry, okay, then you can again have a picture in the following way. So let me, so you have, see, I'm trying to plot these vectors now, the vector 1, 2 and the vector -2, 3, right? So where does the vector 1, 2 lie? If you go by this description, okay, then where is the vector 1, 2? Vector 1, 2 is nothing but
One to the
yes.
One to the right and two up.
Yes, so 1 to the right and 2 steps up, that's 1, 2, or the vector 1, 2. When will it become a vector? It will be a proper vector if I draw this position vector, right? So yes, this is the vector. If when we write it like this, A comma B, then that's just the coordinates or the address, as I like to call it. When you write it like this, it is actually the vector, the position vector of that point. So you have to actually draw it like this, right? Okay, to be very precise. So this is the vector 1, 2, and then the vector 1, minus 2, 3 also I want to write. So minus 1, minus 2, minus 2, 3. So that's going to be minus 2 to this side and 3 up here. So that's that. Okay, almost. That's the point. And then we can draw that vector also. Okay, so slightly distorted, but okay. Oh, sorry, this is just the pen doing its work. Okay. So that's the other vector. Okay, and now I want to find a linear combination, which means I want to find x and y such that x times this first vector plus y times the second vector gives me the vector 1, 9. And the answer that I found here is telling me that if you take x equal to 3 and y equal to 1, right, that was our answer here. X equal to 3, y equal to 1, that should work. What does that mean? X equal to 3 would mean I'm multiplying this vector 1, 2 by 3. So I'm taking 3 times this vector plus 1 times this vector. You know how to do vector addition? So let's
Yes,
see.
ma'am.
Yes, ma'am. So 3 times 1, 2 plus 1 times minus 2, 3. Sorry. Where does that lead us to? Okay, let's see where that goes. So 3 times 1, 2 means you scale the first vector by 3. Correct? 3 times 1, 2 is.
How did you get 3 and
Sorry?
how did you get 3 and 1?
Oh, I just looked at this solution and I'm trying to explain geometrically what it means.
Okay.
Yeah. Yeah. So 3 times 1, 2 means the vector. This is the vector 3, 6. And this is the vector minus 2, 3. Okay, so I have to add these two vectors. So 3, 6, the vector is going to be along the same direction, but thrice the length, right? So along the same direction, thrice the length. Let's say it's up here. Okay, I'm not drawing very precise pictures. And the other vector is minus 2, 3. So that same vector that was still there. And now when you want to add, what you have to do is you have to complete the parallelogram, right?
Drag
So
the
you,
second vector up to the head of the first one.
that's right. So you complete this parallelogram. I hope this is a parallelogram. Looks like one. And then up here, that's your answer. Okay. And so in this case, it's not very difficult to see. You can just add these vectors, correct? And so you know this is 1, 9, which was the expected answer. Okay. So this point will actually be your vector 1, 9. If you draw this. Okay, this is your vector 1, 9. So you can think of this as either intersection of these. So have you heard about linear span?
Yes, it was there in the prerequisites.
Okay, so then 1, 9 lies in the linear span of these two. Why am I saying that? I'm saying that because I could find x and y such that x times this first vector plus y times the second vector is 1, 9. Or the other way, 1, 9 is expressible as something times 1, 2 plus something times minus 2, 3. Okay, so 1, 9 lies in the linear span of these two. Okay, so I hope we got that idea right. Okay, so what did we started with a simple system of equations, 2 equations, 2 variables. We saw that the row expression means you're finding intersection of the corresponding lines, and then we saw the column expression of this. And so we are saying that we can find x and y when this column lies in the span of these two columns. Okay, so why we are doing all this is because now we want to adapt this language going to higher dimensions. Okay, So let me see, if we wanted to do the same thing in three, if we had three equations in three variables, okay, then where there are lines, instead of lines, we would have to draw planes, okay, and then since each equation would correspond to a plane, three equations mean you're looking at three planes in 3 dimensions, okay, and you want to find their intersection. So those kind of pictures are not so easy to draw, right? Here we could easily draw this, but in 3 dimensions, it's not so easy to draw. And in 4 dimensions and all, you can forget about drawing, correct? So then we want to have a consistent language that can take this same thought process to higher dimension. So let's note the following point. Okay. That the coefficient matrix or the columns of the coefficient matrix yeah, to say this, maybe let me say this first. What would have happened if instead of having the equations 1, 2, or instead of having the columns 1, 2, minus 2, 3, if I had the following columns? So I'm going to write that here. Okay. Instead of 1, 2, minus 2, 3, suppose we had started with the columns 1, 2, 2, 4. Okay. Then, and if we had tried to go through this entire process, what would have happened? So the question would have been for us, does the vector 1, 9 lie in span of the vectors 1, 2, 2, 4? This is one way of
It
asking the
doesn't,
question.
since they are the same.
Yes?
Yeah. They are the same direction.
They are the same direction. Okay, so let me just explore that. Your answer is very correct. So let
And if
me
you look
explore
at
this.
the equations, they're actually the same.
That's right. Okay, so in the row form, if you were looking at them, then the equations you would be looking at would be x plus 2y equals 1, and the other equation would be x minus 2y, right? No, so
X
here
minus
x plus
3y.
2y, x plus 2y, and the second equation would be 2x plus 4y equals 9. With these coefficients, these would be the equations that you are looking at in the row form. Okay, and now these are not the same equation, but there is another problem, which is
It will have no solution.
it will have no solutions because this is just a multiple of this.
Both of them are same.
Okay, but this is not here. This is 9 is not the same multiple of this. That is one way you can have a problem. Even if 9 was a multiple of 1, instead of 1, 9, if I had say 1, 2, then also I would not be able to find a solution because it would be the same equation. Okay, so the problem can occur in 2 ways. So the problem can occur both for 1, 9 as well as for 1, 2. The problem for 1, 9 will occur because 9 is not 2 times 1. Okay, so it doesn't even make sense here. And here, even though 2 is 2 times 1, okay, when you write these equations, they are the same equation then. These are just the first equation you multiply by 2. Okay, so these two equations, if you look at them as a line, okay, or you look at them in the column form, either way, wherever you look, you can see that these will be the same equation. Okay, so it's not giving any new information. Yes?
We can We can say that the first equation is multiplied.
I couldn't get the entire sentence.
I am telling that the whole first equation is multiplied by 2.
Yes. Yeah, exactly. So that is what is happening here. Okay. So this here, the problem is that you are seeking two independent variables from one piece of information. Okay. That's the problem that is in the second case. Here, the problem that is happening is that the column 1, 9 is not in the span of the columns in the coefficient matrix. Okay, so these are two kinds of problems that can occur.
So basically, we'll be having no solution in the first one and infinite solutions for the second one, right?
Yes, so in the second one, you could have many possibilities. In the first one, there is no possibility. Okay, so here you will have no solutions simply because 1, 9 does not lie in the span of 1, 2 and 2, 4. And here you will have many, I mean, you could find number of pairs x and y which satisfy these equations because essentially there is just one equation. Okay, so here there will be infinitely many solutions. You take another way of looking at this is, since this is just one equation, x plus 2y equal to 1, essentially only this equation, you take any value of x, you can find a corresponding value of y. Okay, so for any x, there is a corresponding y. So in this way, you have infinitely many solutions in this case. Okay, but I just wanted to stress how the problem occurs. Okay, one of the problem occurs because this is not in the span of these two. Okay, and the other infinitely many solution problem occurs because these two equations are not different at all. They are just multiples of each other. So it's looking like you have two equations, but essentially you have only one. Okay, so we have to steer away from, if we want to have or if you want to say that a system has a unique solution, then we have to make sure that these two things are not happening. Okay, only then the system will have a solution. Correct. And the way to express that is exactly in this language that I have written here. Okay, all this that I have written here in the language of columns or column vectors, that's the language we will take forward. So if the columns of the coefficient matrix do not lie in the same, see, if we were in 3 dimensions, see, okay, let's go back here. Here, in 2 dimensions, what is happening is these two are multiples of each other. Okay, if you draw them, they will just overlap each other, right? Only the length is different, but they are the same vector, same direction. Okay, in 3 dimensions, what will happen is, if you have 3 such vectors, then this problem occurs if the 3 vectors or the 3 planes that they represent, okay, those 3 vectors lie in the same plane. Those 3 planes are the same. Just like here, these 2 vectors are the same. Similarly, in 3 dimensions, those 3 planes will be the same, which is like saying those 3 columns lie in the same plane. Okay, that will cause the problem in 3 dimensions. And in higher dimensions, exactly the same, only the language now becomes lie in the same hyperplane in higher dimensions. Okay, so let me just rewrite this. In R2, okay, in 2 dimensions, this means the columns are multiples of each other, just like what we saw earlier. Okay, then in 3 dimensions, this means instead of vectors, you will have planes, right? You'll have vectors in planes and you will have looked at those planes. So this means that the columns lie in the same plane. Another actually nicer way of saying it is these two columns are collinear here, and here it will mean that they are coplanar, that the columns lie in the same plane. Okay, so here they are collinear.
Kavita,
Yes.
there is a request to repeat what is a hyperplane.
Yes, so I have not, yes, thanks, Nithin. So I have not defined what is a hyperplane, okay, and I'm going to not define it for now. I will just say that it is a generalization of plane. What you have as a plane in R3, okay, in Rn you will have a hyperplane, or you can okay, so a plane, yeah, maybe I can do a little bit. So a plane in R3 will be defined by ax plus by plus cz is equal to 0, right? X where x, y, z are your three directions, a, b, c are the coefficients that determine the plane. Then like this you can go on, okay? And we don't say plane in R4 or plane in R5. For higher dimensions, we use the term hyperplane, okay? So hyperplane is exactly a generalization of this in R4 or R5, or if you like Rn, okay, where n is anything greater than 3. Then the equation will be given by, so now you will have, if I'm saying R4, okay, then I have 4 variables, say x, y, z, w, right? So it will be ax plus by plus cz plus dw equal to 0. This is the equation in R4, equation of a hyperplane in R4. Equation of a hyperplane in R5 would be a, so I will have 5 variables x, y, z, w, u, let's say, plus dw plus eu equal to 0. This is how it will look like in R5. And in general, if I have variables x1, x2, up x3 and so on up to xn, okay, this is happening in Rn now, there are n directions, then an equation of the form a1 x1 plus a2 x2 plus a3 x3 plus dot 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 plus an xn equal to 0 defines a hyperplane. This is the definition, but okay, so I hope that helps at least some of you. But you know, for others who it doesn't help much, or if it's confusing you, then I would say ignore it for now. Okay, just think of generalization of a plane, whatever it is, because I'm not going to go into this geometric picture ahead of this. Okay, only till now I have used this geometric intuition, but my advice to everybody is that once you go to higher n greater than 3, you should just leave behind this geometry. Okay, you should leave behind the thought that you can have geometric intuition for everything. That's not possible beyond 3. Okay, so the thing to do is convert everything to algebra. Okay, and so that is what we are trying to do. So this geometric intuition is useful only up to 3 dimensions. And it is useful because it gives you a clear understanding at least up to 3 dimensions. So I don't say that geometric, you should completely throw away this interpretation or completely forget about this. No, this is very useful because now you could see, you know, this row expression, column expression, the vectors, you can actually see in 2 and 3 dimensions. I'm only saying in higher dimension, don't think that you will be able to imagine it like this. Okay, and in higher dimension, we want to make our language independent of the geometry. Whether somebody has intuition or not, they should be able to work this out. Okay, so that's what we will be doing. Okay, now everything we want to take to algebraic language. What is algebraic language? Algebraic language is exactly this statement here. Okay, that the columns of the coefficient matrix do not lie in the same hyperplane. This whole thing can be expressed by saying that the columns are linearly independent. Okay, so I will just state that. So this statement, so to say that the columns do not all lie in the same plane or hyperplane, whatever it may mean. This is same as saying that is same as saying that the columns are linearly independent. Okay, this is one way of saying it. Or that or you actually put it in one more way. So if A is the matrix that you can make by putting together these columns. Okay, just write the columns one after the other. If A is a matrix obtained by putting, or is the coefficient matrix, let me say, is the coefficient matrix obtained by putting these columns or writing these columns one after the other. Then this linear independence is same as saying that AX equal to the only solution of AX equal to 0. The only solution of AX equal to 0 is X equal to 0. It's a 0 vector. Okay. Now, I should probably explain myself when I write this. Okay. What does this equation mean? A is a matrix, right? This X means X is a vector in whatever dimension. Okay. So let me explain that notation slightly. AX equal to 0. So to be very precise, a number of books will actually write this as capital X. Okay. Because that is also a matrix actually. So AX equal to 0 means the system of equations that you get by, so what is A? Remember, A is the coefficient matrix, right? So A is this matrix here, in which you have these columns. Okay. X means, so X is the vector x1, x2, xn. So this is all happening in Rn equal to 0, 0, 0. So this is in Rn. This is the 0 vector in Rn. Okay. And this is my n cross n matrix, coefficient matrix. Okay. Don't worry if you this seems a bit difficult. We will do a concrete example, then things will be clear. Okay, but I'm just trying to explain my notation here. So let's actually quickly do one concrete example. Okay, and then come back to the general things. All right. So suppose you have now 2 by 2, everybody knows, right? So let's look at a 3 by 3 example. So I'm going to give you a system of equations. So let's say 3x plus 2y plus z equals 5. So I would actually encourage everyone to take your pen and paper and solve this one with me. Plus 2 equals 6. Okay, and 3x plus 3y plus 3. This should have been 2z. 3z equals 7. Okay, so some system of equations is here. and we want to find, like before, we want to find x, y, z that satisfy these three equations simultaneously. X, y, z satisfying okay. Now, just like we had, imagined in the two-dimensional case, this each of these is a plane. This is what I was saying. See, each of these is a plane, right? Yeah. So, oh, by the way, I think I made one small mistake here, which you might not have caught, is that you could have a non-zero element here. Just for, posteriority, I will correct this, but this is not going to affect anything for now. Just say plus some k. Okay, let's leave it at that. Yeah, so these are three equations, okay, three planes, and we want to find x, y, z that lie on all three, which is like saying we want to find the intersection point of all three. Now, in this column notation that we have seen, we will actually write this matrix. Okay, so let's write the first column, which are coefficients of x. So the first column is 3, 2, 3. The second column is 2, 4, 3. The third column is 1, 2, 3. Okay, this, and now here we have our variables x, y, z equal to 5, 6, 7. Okay, so this ax equal to 0, right? That notation, that so this is my A coefficient matrix. This is the vector x of variables. Okay, and this we will call some vector b. Okay, so that now this system of equations I can abbreviate instead of each time writing the whole matrix. If I just want to quickly say it, I will abbreviate the system of equations as ax equals b. Okay. So finding x, y, z satisfying these three equations is the same question as solve the system ax equal to b. Okay, so now we have translated this to this language. And I said earlier that you can solve this system if, first of all, this has a unique solution if, first of all, these three columns are linearly independent. Second of all, B lies in the linear span of these. Only then such x, y, and z can be found. Right? So, is there some kind of noise?
Yeah, Nishit. Yeah, now it shouldn't be there.
Okay, okay. So now we are looking at, so you can do this check independently. Okay, so this I'm not going to check for you. This is maybe an exercise for you. 3, 2, 3. This column, and this column. Okay, these three columns you can check are linearly independent. Okay, and now actually from some, because I know linear algebra, I know that these are three linearly independent vectors in R3. So they span all of R3. So this B lies in their linear span. And so this will have a solution. So whatever I said just now, okay, all this, if you know some linear algebra, and if you have been doing this, span and basis and this kind of thing, slowly you will get a hang of this. Okay, so I will write the statements here. Later I will write it down. It will take some time. So I will write that argument here. But even if you don't know it for now, I'm saying let it be. Okay, leave it for now. Essentially what I'm saying is this system of solution, if you show that these three columns are linearly independent, it will have a solution. Okay. Now the question, now we are going to move from the question of when it has a solution to how to find the solution. Okay, so how to find this solution? Now, have you seen these three equations in three variables in school? A quick raise hands. How many of you have seen 3 equations in 3 variables in school by now? 2, 3, 6. Okay, so a number of you seem to have seen it. Okay, approximately half of you. Half of you have seen how to solve 3 equations in 3 variables. Okay, all right. So then, since the remaining half of you have not seen it, I'm going to go through the details of this solving. Okay, now to do the details of this solving, I should remark here, okay, that we could have solved this in another way. This process I'm going to show here once. Okay, so what I could have done in order to solve this system of equations earlier was looked at this coefficient matrix. I want another color. Yeah. So let's look at 1, 2, -2, 3. Okay, and since I am interested in this particular vector 1, 9. Okay, I'm going to just put it here and call this this is called the augmented matrix. Okay, so I want to have a shorthand notation instead of writing all this every time. I just want a shorthand because I'm basically interested in dealing with these numbers. Okay, so that's why we have written it like this. This is called the augmented matrix form. Augment means to this you just adjoin this here in the end. Now what we'll do is we will keep the first equation fixed. Okay, geometric picture, we keep the line x minus 2y equal to 1 fixed. Okay, and what we'll try to do is this second line, okay, this line, instead of looking at this line, which is dependent on 2 variables x and y, we will try to eliminate one of the variable. Okay, now eliminating a variable in this situation in the geometric picture means making this line parallel to one of these axes. Okay, if I eliminate the x variable, that's like saying I'm going to make this line parallel to the x-axis. Okay, and if I eliminate the y variable, that's like saying I'm going to make it parallel to the y-axis, so that only the x coordinate matters. So eliminating a variable is like making this line parallel to the x-axis. So now what we seek geometrically, if you want to look at the idea, what we are seeking is a line that is parallel to the x-axis. If I want to eliminate x, parallel to the x-axis passing through the point 3, 1. Now what is that line parallel to x-axis passing through the line 3, 1? Is this line, right? So what we are going to say is that the intersection of, if you wanted to find intersection of these two lines, that is same as finding the intersection of this new line and x minus 2y equal to 1. Right? Geometrically, it is clear that this is the line that you have to consider. Algebraically, how do we get there? In the following way. You want to eliminate x, right? You want to eliminate the x variable. That means you want to eliminate this. Okay. Now you want to eliminate this. The way to do it using, and you want to have it the same, have the resulting thing, the same intersection with 1 minus 2. Okay. So you do it in the following way. This is called as a row reduction. What you do is you take, so this is my row R1, this is my row R2. What I'm going to do is I'm going to make a 0 here. This has to become a 0 in the resulting thing. I don't want to change my first line. So the first line stays as it is. Now, if you want to make this 0 and use only operations such as row subtraction or row plus some constant times the other row. Okay, so then so I will detail out these steps in a moment, but let me just do it here once. So what I'm going to do is I can see that if I do 2 minus twice 1, I will get a 0 here. Okay, this 2 minus 2 times 1 will give me a 0 here. Okay, and so what I will do is that operation I'll apply to all of R2. R2 minus twice R1. Okay, so now if I apply this operation in the first spot, of course I get a 0. That is how I designed this. Now I apply the same operation here. So 3 minus 2 times minus 2. Okay, so what is that going to give me? 3 minus 2 times minus 2. So that's 3 plus 4. That's going to give me 7. Okay, and the same operation I have to apply here. 9 minus 2 times R1. So 9 minus 2, which is going to give me another 7. Okay, so this is what I have. 0, 7, 7. Okay, so if you think in terms of lines, what is this line? This line is the line 7y equals 7. Okay, or this is same as y equal to 1.
Ma'am, Ara was asking, can you please repeat this again?
Yes, yes. So I will, so all I'm doing here, Ara, is trying to, reduce this. See, I'm trying to get to this idea that instead of looking at this line, I want to eliminate one variable and instead look at a parallel line intersecting with the first line. I still want to get this point only. Okay, I still want to get this intersection point. But is there a line that I can use that's parallel to the x-axis or y-axis? Some other line will also work. Instead of this one, we are trying to locate this line. Okay, now I'm not telling you the details of how we are locating that line geometrically. I'm telling you the details of how we are doing it algebraically. What we are doing is we are trying to get a 0 in this spot. Okay, to get a 0 in this spot, if the only operations, okay, why only these operations? That's a deeper question, and maybe we can talk about this in some tutorial, because they have to be something called as linear operations. Okay, so only 2 operations are allowed. One, you can actually in some sense only one operation is allowed, which is take a linear combination of the rows, some linear combination of the rows. Okay, so if you're just allowed to take linear combinations of rows, then to make this 0, what you'll have to do is subtract twice this from this, right? So this 2 minus 2 times 1, so you're somehow using the fact that this is 1, you're using it to make this 0. Okay, so 2 minus twice 1 is 0. Since you did it here, you have to do it for the entire row. Okay, because this is a row operation, this is not just element. You don't want to change your original system. You still want to stay in that, have the same system. Okay, so you do the operation for the entire row. So 3 minus twice this will give me 7. 9 minus twice 1 will give me 7. So now instead of looking at the equations x minus 2y equal to 1 and 2x plus 3y equal to 9, which will give you intersection 3, 1, you're looking at the equations x minus 2y equal to 1 and y equal to 1, which also give you the same intersection 3, 1. This is the line y equal to 1. Okay, so what you have done now is you have eliminated one variable. Okay, that elimination of one variable in geometry terms means you're making something parallel to one of the axes. Okay, and that elimination makes life easy for you here in this case, because this now when you put this back into your original form, this was the augmented form here, correct? Now this means that 1 minus 2 0 7 x y equals 1 7. So now if you want to solve this, when you solve this system, if you suppose you multiply the second row first, you get 7y equals 7, so y equals 1, and then y equals 1, if you substitute in the first equation, that will give you x equals 3. Okay, x minus 2y equals 1, you substitute y equals 1, that gives you x equals 3. Okay, so what this eliminating one variable, what did it do for us? Why was it useful? Because in the last step, you had a 0 here, and so it sort of simplified this last calculation. This calculation was simplified, so the earlier equations calculation was also simplified. Okay, you just substituted and found x. Okay, now this whole process, which was we did it for 2 variables, I'm going to do it for 3. Okay, so now in here, what we are going to do is look at the coefficient matrix. Okay, look at the augmented, because we also need to take care of this vector b. So we look at this augmented matrix, okay, and do the same process as before. Now I'm not going to worry about the geometric picture at all, because I would have to be very good at drawing and everything to be able to express these planes and then make it a parallel plane and so on. Okay, so let's not worry about the geometric picture at all. Let's just make sure that we do row operations. Okay, you are allowed to do only linear combinations of rows. Okay, and now what we are going to aim for is to make this element 0, this element 0, and this element 0. Okay, why? Well, this is what is called as the diagonal of the matrix. This is a square matrix and this is its diagonal. Okay, we want to aim to make everything below the diagonal 0. Okay, so that means these 3 entries we want to make 0. Okay, so our aim is below diagonal elements should be 0. And we want to use only row operations. Okay, so that's where we are going. So, can anyone help me here? Now, if I want to make this element 0, and I'm telling you that I want to use this. Okay, so I want to do R2 minus something times R1, so that what will happen is the first thing I want to leave unchanged. R1 I want to leave unchanged. Here I want a 0.
Make it 2 by 3.
Yeah.
2 by 3. Okay, so if I do 2 by 3 R1, then I will get 2 minus 2 by 3 times 3. So that's going to give me 2 minus 2, which is 0 in this spot. Okay, now, but this operation has to be carried through for the rest of the elements also. Okay, so let's carry it through for those remaining elements. You can do it. So here, for example, you will get 8 by 3. And here 4 by 3. Yeah, and this is 2. No, is that right?
Yeah, it's true.
Yeah, what do we have here?
We'll have 2, right?
2. Okay, all right. So we have that. And for now, I don't want to confuse you, so I'll just leave this row as it is. So what we have achieved is we have a 0 here. Okay, and since we did it
I
uniform,
think that's not 2.
it's not 2.
Yeah, it should be 8 by 3.
8 by 3. Okay, 8 by 3. Okay, so the point now is that you have done a row elimination like this. So you have transformed this entire equation to this. Okay, and because you did that, now you did not change the point of intersection. Okay, you only eliminated one variable. Now what we want to do is eliminate these two. Let's do it one by one. Now you don't want to be in a hurry, because if you are in too much of a hurry, you might end up, first of all, you don't want to touch this. You have this 0, it's precious, leave it there. Okay, and now you want to make this 0. Let's do it one by one. Okay, so what's the best way of making this 0?
Subtract the first one.
Yeah, so now let me do this. Let me do R3 minus R1. Okay, it looks easy now. So here, the rest of the elements we are not touching. Second row also we are not touching. Third row, I'm going to do R3 minus R1. So third row minus minus first row. So 0, 3 minus 2, 1, 3 minus 1, 2, 7 minus 5, 2. Okay. We are almost there.
Now we have to subtract second from first, because if we subtract the first, then it will disturb that 0.
Second from first.
Sorry, second from third.
Yeah, or the third. Yeah, that's right. So you want to make this 0, but you don't want to disturb these, right? So the best way, see, if you do an operation with R3 and R1 again for this one, then that will, remove this 0. You will lose this 0. You don't want to do that. So you do the operation with R2 now. Okay. So that was the idea that you expressed. So let's do it. So we want to do R3.
Ma'am, can do 8 by 3.
Yeah, tell me. Sorry. Were you telling me what to use?
R2.
Yeah. He is put it in the chat. Your voice is breaking down. He's saying we should do 8 by 3 R3 minus R2.
Yes. So R3 minus
8 by
8 by 3 or 3 by 8? 3 by 8 R2, right? Because you want to make this one, this chap, you want to make 1 after this multiplication, 2. Subtract from this to give 0. Yeah. Okay. So first row as it is. Second row as it is, no change. Third row is what we are seeking to change. 0. This we designed to make 0, right? This is our design. And now we have to find what comes here.
1.5.
1.5
And 1.
Oh, like, is it okay if I write 3 by 2 or something? Yeah.
yeah.
Okay. So now we have achieved our aim. We have 0, 0, 0 here. In this, what we did is we eliminated the first variable. In this, we eliminated these 2 variables, in fact. Now this is an equation in 1 variable, right? So we started with this system of equations, used this process. This process is called row reduction. Okay. So this is the row reduced form. Row reduced form. Okay. And now this row reduced form, once I have these 3 zeros, it is easy to solve the system of equations using this. Okay. So now I will rewrite the system of equations using this row reduced form. What is my system of equations? It is 3, 2, 1, 0, 8 by 3, 4 by 3, 0, 0, 3 by 2 times x, y, z equal to 5, 8 by 3, 1. Okay, this is the system of equations that I'm solving. Okay, and now let's start from the last one. This tells me 3 by 2 z equals 1, which will imply z is 2 by 3. I got z. Now from the second row, I get 8 by 3y plus 4 by 3z is 8 by 3. This implies 8 by 3y is 8 by 3 minus 4 by 3, and I know z is 2 by 3. Okay, so this you can simplify to get y. Correct. Now you have y and z. Now you look at the first row and write down the first equation. You have 3x plus 2y plus z equals 5. You've got z, you've got y, you can solve for x. right? So you can solve, and later if you want, you can tell me what is this answer. So in this way, you got your x, y, and z. You got the solution to this system of equations. Okay, so geometrically, the idea is that you are eliminating certain variables and reducing the number of variables in the equation, so that, in the end, if you have a form like this, then this last thing will be one equation in one variable. The second last will be two equations in two variables, of which one you have already solved. The next will be one equation in three variables, of which these two you have already solved. So only one left. So at each step, you have essentially one equation in one variable to solve. Okay. And this entire row reduction process is designed in such a way so that the point of intersection of these three equations is same as point of intersection of these three equations, same as point of intersection of these three, and so on. So in the point of intersection of the beginning system of equations is same as the point of intersection that you have here. And so the solution that you obtain to this reduced system is same as the solution that would be for the original system.
Ma'am, what are the valid operations?
Valid operation is simply this, taking a linear combination of rows. That is the valid operation.
Ma'am, will this work for
Arav is
any
asking-
number of variables?
So you can add the rows also.
You can add the rows. So I will tell you one guideline. So one thing is that we want to make this below diagonal elements 0, right? And this is unchanged. The first row is unchanged. So always what we'll do is, when we are eliminating these elements in the first column, we will use this element for the elimination. See, that's what we did, right? We used that 3 up here for eliminating and creating this. And for this 0 also we used R1, that is this 3. Okay, so this element is called the pivot for this step. Okay, so this is our pivot for step 1 or the first column. Okay, so pivot y. Sorry, why is it not writing? This is pivot for first column, because that's the one, sort of the anchor you're using to make these elements 0. Okay, now when you want to make this element 0, okay, here, this one you want to make 0 in this last step, right? What is the anchor that you are using? You don't want to use this, because if you use 2, you are disturbing this 0. Correct?
8/3.
So you're using 8/3. So for the next step, okay, or for the second column, your pivot is 8/3. Okay, so that's the nomenclature. Okay, so this is your pivot for the second column. Pivot for, you will require this name, okay, because tomorrow when Nithin talks about takes this ahead, these pivots will play a very important role. Okay, yeah, is this process, I mean, algebraically at least, is the process clear? I'm hoping that
Explain
the pivot. The pivot
sorry.
part, can you explain it again?
Yeah, the pivot means the non-zero element that you used to make these 0. So when we are making this one 0, we did R2 minus 2/3 R1, right? So 2/3, where did 2/3 come from? It was this element by this element. This element divided by this element, correct?
Oh,
Then,
okay.
Then when you wanted to make this 0, what you actually did is R3 minus R1, but you can also view this as R3 minus 3/3 R1. Okay, 3/3 means 1. If you want to view everything in the same way, you can view this as R3 minus 3/3 R1. So you are always dividing by this pivot element. here also, okay, what you did was, you want to make this 0, so you did R3 minus whatever element is here, you divide by that element. But dividing by 8 by 3 is multiplying by 3 by 8, so that's how you got it here. Okay. So we are always dividing by the pivot element. I will stress that point when I list down the steps. Okay. What you're essentially doing is, if you want to kill this element, make this 0, you're doing this element minus this element by 8 by 3 times 0, times R2. Okay. In general, if this much is clear, let me write now the general formulation.
Ma'am, will this work for any number of variables?
This works for any number of variables. So what I'll do is, now, if you have never seen the general matrix written like this, then I'm going to go slow and just write a 3 by 3. Okay. So the notation 1, 1, this suffix 1, 1 means first row, first column. So A1, 1 is the first row, first column element of the matrix A. Okay. A1, 2, first row, second column element. A1, 3, A2, 1, A2, 2, A2, 3, A3, 1, A3, 2, A3, 3. Okay. This is my matrix A. This is my variable, okay, or the vector X. X1, I can write X1, X2, X3, or I can write X, Y, Z, whatever, equal to the vector B. Let me call it B1, B2, B3. Now this system of equations we write as the augmented system A11, A12, A13, A21, A22, A23, A31, A32, A33, augment the column B. And now you start the process of elimination. Process of elimination is that you want to make this element 0, this 0, and this 0. Sub-diagonal elements, which means elements below the diagonal, you want to make them 0. First step, you make this one 0. Okay. So you make that one 0 by doing what? You do R2 minus, I don't know what is A21, right? Some number. So any guesses what I should subtract it from, or subtract from it to make it 0?
A21 by A11.
A21 by A11 times R1. Now, if I do this R2 minus A21 by A11 R1, then when I am applying it to this first column here, these two elements, okay, that's going to give me a 0 here. Right? Now, I don't care what I get here in the second spot. I will just call it A22. I'll put 1 to say that this is what I got at the end of the first step. This number has changed. Okay, this is not the same as this after you apply this operation. Correct? So this changed number I will denote by, or you know, since we don't really care what this number is, I'll just put a star. Okay, whatever, something, you've got something here, something here, something here after the reduction. Okay, you did not touch row 3, so row 3 right now is as it is. Okay, the next step I want to do is, I want to make A310. How would I do that? This is going to remain as it is. This has become 0.
Excuse me, ma'am.
Yes.
Sorry to interrupt. Just a reminder, we have about 5 minutes.
Yes,
to
yes,
end this.
I do know. I am aware. Thank you. So I'm just asking, so how does this element become 0 now? I have to do R3 minus something, right? And I want to use A11 as the pivot, remember?
minus A31 by A11.
Minus A31 by A11 are 1. That's right. So this is a 0. This will change. This will change. This will change. Okay. Now, when I'm dealing with the second column, I actually need a name for this element. Okay, because this is the pivot. So now I'll give it a name. Okay, let's give it a name. Let's give it the name A221 something. Okay, because that was at the end of the first step of the algorithm or whatever process. So this is my A221. Okay, and this has this at the end of this process is some A321. Okay. Something. Okay, and if you are too worried, I mean, you don't need to be too worried. It's just that you know, these elements are different from the elements that you started with. That is the only thing you need to keep in mind. That now they have changed. They are not these two same elements. Okay, so you can call it anything you like, but just notice that they are different from what you started with. Now you want to make this 0. Now what will you do? You have A11, this one as it is, B1, this one is as it is. Here you got 0, here you got 0. Here you have A22 prime, something here, something here. Okay, now you want 0 here. So for that we will do R3 minus
A32 by A22.
A32 prime.
Yes.
Yeah.
By
Yes,
A22
A32 prime by A22 prime. So this is your pivot now, correct? That is the one that you're putting in the denominator. Star something, something. We don't know what those numbers will be. Will be some numbers which will be used to solve. But the point is the zeros that we wanted to get here, we have got. This is the general process. So I have expressed it for you in the 3 by 3 case. Okay. Now what I will do is, see, we are out of time, but the same process in the same way can be carried over to n by n, any dimension matrix. Okay. So what I will do is, I will, first of all, I will complete these notes. Okay. These notes I will share after maybe half an hour or so, where I will complete this and write the general formulation for n cross n. Okay, but you should remember that the steps are the same. Now what we would like to see next is see how these operations that I mentioned here, these row operations, these are called row operations. Okay, these row operations can actually be expressed as some matrix multiplication. You are multiplying this original matrix by some matrix on the left to actually give this reduction. Okay, so that is the next step in our study. Okay, this process is called as Gaussian elimination. Okay, so we are trying to write down the general formulation of Gaussian elimination. Okay, and so I've tried to write it down here for you for a 3 cross 3 system. Similar thing you can do for n cross n. I will complete these notes for you. Okay, so yeah, so it's 4 o'clock. I will stop for now, but if there are any quick questions, I can take them.
Yeah, Arav had a question in the chat. If we have systems of equations consisting of 5 or 7 variables, wouldn't this method be time consuming? And Raghav had replied that I think for us, but not a computer.
Yes, for us it would be, but not for a computer. That is absolutely right.
And there were some questions from Sarth as well.
Yes.
Is there an analog of Gaussian elimination for matrices with entries in a finite field?
That's an interesting question. So I have never thought about it because I've never come across it. But yeah, I will I would like to maybe I will find out something.
And also Gaussian elimination for Laplacian and quadratic or near quadratic matrices.
So this is actually see, Laplacian as a if you mean as a matrix of numbers, we have calculated the Laplacian of something at a point, then it's simply a matrix of numbers. Okay, But if you're thinking of the Laplacian with variables in it, okay, so then you want to see whether you want to have a linear process there. Okay, so these are linear processes. All this is happening in the domain of a vector space and linear transformations. So linearity is what is being preserved here. If that is sufficient for your application, then you can also apply to those matrices. Okay, but it is not entirely clear to me what you mean here by Laplacian matrix or quadratic what?
I think he meant the Laplacian of a graph. He actually mentions it, that he has seen some efficient algorithm to compute the Laplacian, to do Gaussian elimination on Laplacian matrices of graphs. I think I did a Google search actually, and so yeah, there is.
But possibly then, because those matrices are similar, symmetric.
Yeah, I think these have some special
That
structure,
might
so you can
play
do
a
it
role.
better, essentially.
Yeah. So so in that sense, I mean, if the matrix has a special structure, like if the matrix is symmetric or something, then this process can be speeded up.
Yes.
So I hope we will be able to talk about a little bit about it in the coming days.
Yeah.
Any other question?
I don't think so.
Okay, so if there are no questions for now, then I see Nithin and I will share a problem set with you, where we will encourage you to actually solve a system of equations by hand like this, especially people who have never done it before. Just get a hang of this row reduction process, okay? And then maybe Adityan can also help you out. We will give him some set of problems, and then just get a hang of this, because tomorrow, see, one of the main things in our pivoting process just now was that those pivots were non-zero. Okay, and so you could divide by them. I was assuming they are non-zero, and so you are dividing. And then we have to consider the case, what happens if they are zero. So that process has to be clear in your mind before we go ahead to the next step. Okay. So try to solve at least like one or two systems of equations by hand. We will give examples, 3 by 3, maybe a 4 by 4, okay, where you do row reduction by hand to get that subdiagonal elements 0. Okay, so you'll get a hang of it that way.
Okay,
Alright?
ma'am. Yeah.
Okay. So all of you tomorrow.
Yep. Thank you.
If there are, in your study, if you come across questions, you can of course ask Aditya. You can also leave us some questions by email or something. Or you can collect, one of the volunteers can collect and ask. That is also fine.
That sounds good.
Okay, thank you, Sai. Thank you all
Thank
of you.
you.
Yeah.
Thank you.
See you tomorrow. Yeah.
Thank you.
Thank you, ma'am. Thank you, sir.
Bye.